The observability of the controllable canonical form. Now, we saw the controllable canonical form before. And if you recall, because of similarity transformations, even when I do a similarity transformation, the transfer function here, h of z, is the same regardless of which set of coordinates we use, whether the original coordinates or the transform coordinates. We get the same transfer function. Because of the Kalman decomposition, we only have the controllable and observable parts of the system working with. So, actually, the original transfer function still only has the number of states associated with the controllable and observable parts. What happens to the other states is that you get pole zero cancellations, and so those actually go away. Now, in the single input, single output system, if our system is controllable, we can put it into controllable canonical form. Okay, so this is a standard form. Here's my A and my B, and in general, I'll get this C matrix and D. So we want to check now to look at the observability. How does the observability relate to this controllable canonical form? The system is already controllable, so the question is, is it observable? Now, the companion matrix is a very special form. So not only is it a standard form, but it's a special form. In particular, the eigenvectors of the companion matrix are of this form. So C subscript n. So this is the Greek letter C. Sometimes people just call it pitchfork. So pitchfork subscript n means you take the value that you're applying and you take it and its powers. So this is the 0 power, the first power, all the way down to the n minus first power. Okay, so the companion matrix, if it has an eigenvalue lambda, its eigenvector is of this form, where z is equal to lambda. So if you actually multiply it out, so you take this matrix, multiply it out. When you multiply this out, notice that this row times this column is going to pick off the second element. The next row times this column is going to pick off the next element, and so forth, all the way down to this row times this column is going to give that. That doesn't appear in here. So where this row times this column comes in is the fact that the characteristic polynomial for the system, so remember these coefficients are the coefficients of the characteristic polynomial. Since lambda is a root of the characteristic polynomial, then if I plug lambda into the polynomial, I get 0. But this is the polynomial evaluated at lambda, so I can solve for lambda n. And lambda n is all of this stuff. Notice I get all these minus signs, minus the coefficients times the various powers of lambda, and that's exactly what you get when you multiply this row by this column. So notice that this now is equal to this, but this is exactly lambda times this. And so we see that this, in fact, is an eigenvector of the matrix A. Okay, so we have that. Now, it can be shown that the controllable canonical form can be written this way: D plus C, Zi minus A inverse B. So this is Z. Incidentally, I'm doing this in the discrete time. I could also do it in continuous time. So here I have this, and so I'm going to call this polynomial C of Z, this polynomial down here A of Z. Okay. Now, the order of the system is independent of D, and for now we're going to assume D is equal to 0. We'll come back and see what happens when D is not 0. So I have this polynomial, C of Z over A of Z. If lambda is a 0 of this function, then C of lambda is equal to 0, which is equal to this times this vector. Right? So this row times this column is actually C evaluated at lambda. This, and if at a pole, if lambda is a pole value, then A of lambda is 0, in which case I have this row times this column. So notice I have n plus 1 here because I have this denominator in general is of order greater than the numerator. So I have this. But remember, this is actually an eigenvector. And this is kind of like an eigenvector, only it's larger dimension. Okay, so what happens when C of lambda is equal to 0 and A of 0 is equal to lambda? So this is a pole and this is a 0. In terms of the transfer function, we get a pole-zero cancellation. Okay, so in terms of the state model, what's happening? Well, we know A times C of lambda is equal to lambda times C of lambda, and C times C of lambda is, in fact, C evaluated lambda, which is 0. So what is this saying? This is saying that C, which is not 0, it doesn't matter what lambda is, C is not 0, because that first element is 1. So this A times this vector is equal to lambda times this vector, and C times this vector is equal to 0. This implies that you have an unobservable mode. Okay, so remember, the system is controllable, but here we've seen that it is not observable. So we have an unobservable mode. So we have been able to examine the system and see how a pole-zero cancellation corresponds to an unobservable mode. What happens now if we have D not 0? So in this case, we have D plus C over A. Putting it all over a common denominator, we have this. If, in fact, we still have this, then this is 0, the whole numerator is 0, and we still get a pole-zero cancellation. So it didn't really matter that you had the D or not. Okay, so having the D originally gone just simplified things, but it doesn't change the underlying problem. Theorem 25.1 says a state space realization of a single input, single output transfer function is minimal if and only if it is controllable and observable. Okay, and so that's the important thing. So if the realization is not controllable and observable, then we can form the Kalman decomposition. This will yield a lower order realization, contradicting the assumption that we have a minimal realization. A minimal realization is a realization that is as small as possible. On the other side, if the realization is controllable and observable, then it can be transformed into the controllable canonical form, in which there are no uncontrollable modes. This shows that there will be no pole-zero cancellations, and thus it is minimal. So that is Theorem 25.1. Stay tuned for some practice problems.